last week what I did was I went over partial differentiation and partial integration for my students in my workshop. We'll do that together really quick just so we're all on the same page. But if you have an equation that, for example, is f of xy, and that equals xy plus x squared plus y squared. So in this equation, let's say that I wanted to know what the partial derivative of x was, or the partial derivative of this function with respect to x was. This is one of the notations you might see for that, where you have f with little x. So what this is saying is f with the partial derivative of x. And you're going to go through and you're going to differentiate each term with respect to x. Remember that derivatives and integrals jump over addition and subtraction signs. Since they're summations anyways, they're already addition and subtraction, they distribute across. So in this case, we have the partial derivative of x with respect to xy. So the y in this case is just like a 2 if you had 2x. It doesn't matter. It's not an x, so it's not going to change. So the y comes down. And that's because it's attached to this x, and we'll see that here in a second. And this x, the derivative of x, is just 1. So we have just y times 1. And then this one, derivative of x squared, we know is just 2x. Now here's where it gets interesting. This is a constant, but there's no x that's attached to this constant. So when you take the partial derivative of this y squared, it's just a constant. Derivative of the constant is 0. So in this case, this one equals 2x plus y. Okay, so we have two directions we can go from here. We can take a partial derivative of y next, which is what we're going to do, and then we'll come back and we'll take a partial derivative of x. The reason we're going to do both of those things together is because we want to make sure we know how to take sequential partial derivatives and sequential partial integration, which we'll come to, because it does matter, especially when you're dealing in differential equations with things like the heat equation. You will experience certain situations where you'll have to take double derivatives respectively, where you do one and then the other. That's not for the heat equation, but there are PDEs where you have to do that. The heat equation, thankfully, is just double derivatives in the same direction. But anyways, a little off topic. Let's go ahead and finish this out. So we're taking the partial derivative of x first, which we did, and now we're going to take the partial derivative with respect to y from this equation. So here, in this one, this does not have a y term, this 2x, right? Since 2x doesn't have a y term, that's just going to turn to 0. Just like here, this y squared didn't have an x term, so it turned to 0. And so now we just take the derivative of our y, which is just 1. So this equals 1. And this equation is really nice to explain this stuff just because it does work out so nicely in every case. The only thing I don't like about it is that later when we do f of yx, it looks like they're the same. And in this case they are, but they are not always. The order here does matter. And to illustrate that, let's go ahead and further go to f with a partial of y. So we're going back to this original f equation. We're taking all of it with a partial of y. So here, we still have this xy term, which is coupled, so we're good, it's multiplied. So we can just take the derivative of y and treat x as a constant here. So the x carries down, and the derivative of y is just 1. And now we go to our next term, which is x squared. There's no y multiplied or inclusive anywhere in this term, so unfortunately that's just going to be 0. Or maybe it's fortunately, who knows. I shouldn't use those adjectives. Next we have this y squared, derivative of y squared with respect to y, just 2y. Nothing crazy fancy there. So expectedly we get 2y plus x. And now if we were to take the partial of this one next with respect to x, so f of yx, you'll see it does actually work out to be the same as this. That's just a coincidence with the way this equation is written because it's a symmetrical equation. But it does not always work that way. So our partial of this function here with respect to x, we get a 0 and a 1, which equals 1. Now let's go back to this one and take a second partial derivative with respect to x. And we get the partial derivative of 2x with respect to x is just 2. And the partial derivative of y with respect to x is 0, so you just get 2. And you'll see the same thing happens here just because of the way this one's written. In a different equation, for example, if we had g of xt, where we had cosine of t plus t sine of t plus, or I should do x here, so that way something interesting happens. X sine of t, and then we'll just say plus x. I think this one will work out a little differently. So let's do g of x, so cosine of t with respect to x is 0. And then here we have x times sine of t, so the x turns into a 1. And the sine of t is just a constant, doesn't change. Then we have plus derivative of x with respect to x is just 1. So this one works out to 1 plus sine t. Now if we did g of xt, because we're using x and t in this case, so now we're going to do the derivative of this new equation with respect to t, right? So we're going to do derivative here of 1 is going to be 0, and then derivative of sine is cosine, and so we get cosine of t. Now let's hope that this one does actually work out the way I was hoping it would. I just kind of created this out of nowhere. So we're going to take our original function and we're going to do a derivative with respect to t. So cosine of t derivative is going to be sine of t, negative. And then we have x sine of t here, so you have plus x, and then derivative of sine of t is cosine of t. So you can already see this one's definitely a little different, at least in the first stage. And then our final one's just x, that's plus 0. So then this one equals x cosine of t minus sine of t. And I just changed the order so we don't lose our negative somewhere in there, right? Okay. So now we're going to take the partial here, t of x. So now we're going to take the partial with respect to x of this last function. So here we have cosine of t. Oh my goodness, this one's going to work out the same. That's unlucky. Man, this is a bad example, but it's fine. Partial derivative of x cosine of t, x turns into 1, you get cosine of t. Partial derivative of sine with respect to x is 0. So in this case, it also worked out to be the same. I promise it doesn't always work out that way. I'm just writing functions that work out that way, and I apologize. Okay, partial derivatives. Pretty straightforward. Keep the order straight, and then remember, when they're multiplied together, that's when you do, you treat the y as a constant. Well, you always treat the opposite as a constant. But when they're multiplied together, that's when you keep that constant. When it's just by itself, it's the same as taking the derivative of like a 2, for example. That'll just go away. It'll become 0, I should say. Be a little more explicit in my words. Okay, so next we're going to cover partial integrals real quick, and then that'll let us start talking about double integrals. So partial integration is very much the same as partial differentiation. By which I mean it's almost identical. So if we have the integral, we're going to use indefinite integrals just for this part because I think that's easier. So the integral of, for example, x and y, and let's say we want to take that with respect to x. Exactly like in our partial derivatives, this y is treated as a constant in this case. And so if you have constant times x, we know from calculus 2, and actually probably end of calculus 1 depending on your curriculum, that you can pull that constant outside of your integral. And so now I just have x dx. Integral of x, we know is x squared. So you have x squared over 2 times y plus c. That one works out pretty straight. This next one, let's think about the same idea, but let's say we just have theta and dr. So in this case, theta is still a constant with respect to dr, but now we just have nothing. But the integral of nothing is still something, so we can't just neglect it. So this is actually really just theta times 1 dr, so this is 1 dr, so you actually have theta times r plus c in this case, right? So all that to say, even though in taking the partial derivatives and stuff like that, the constant goes to 0 when it's not directly attached to a variable of respect. In this case, it actually doesn't matter if it's in attached to a variable of respect. You're still going to take the integral, and the integral of a constant is now a linear function, right? Okay, that's really all we need to talk about for partial integrals because we're going to use a lot of them here in double integration and triple integration, so it should all work out pretty nicely.